We're going to go ahead and pick back up with factors that influence protein activity. And the one that we're going to talk about on this slide are a couple of environmental factors that can affect how well a protein functions. I do want to point out before we dive into the two that are showcased here that this is not an all-inclusive list. There are other environmental factors that can also exert an effect, but these are probably two of the most common that we see, especially related to human physiology. One of those factors is temperature. And kind of what we find with protein activity is that typically protein activity will increase as temperature increases up to a point. We see sort of this plateau, but then once we get to higher temperatures, it doesn't maintain. Instead, it has this very sort of steep drop off on the other side. So there's kind of this ideal, I guess you could say, temperature window right here where this peak is at. This would be your ideal. Anything cooler than that is going to have a slower rate of protein activity. And then above that, it's going to diminish greatly and then eventually kind of get to a point where you're really not getting any function at all. So what's going on here? At these cooler temperatures, I'll go ahead and write this in blue since it's on the colder. What we find at these cooler temperatures is that the reason we're getting a decrease in protein activity is due to the ligands moving slower. Sometimes the proteins themselves are moving. Some of them are stationary, some of them move. But the proteins and the ligands are moving slower due to less kinetic energy. That's what temperature is a measurement of, remember? So we got to remind ourselves that temperature measures the average amount of kinetic energy in a system. And the amount of kinetic energy that something has, kinetic energy is the energy that is associated with motion. So if something has more kinetic energy, then it's moving quicker. If something has less kinetic energy, then it's moving slower. So at lower temperatures, substances possess less kinetic energy, and they are moving slower as a result. So if the ligands themselves are moving at a slower pace, it's going to take longer for them to hit the binding site that they need to bind to change the protein's activity level. And that's why we're going to see lower rates of protein activity. It's just it's taking longer for the ligands to get to the binding sites. But what about this higher temperature? I mean, one would think that if lower kinetic energy means slower and that means diminished activity, that greater temperatures would always be better. But clearly we don't see that's the case here because this significant drop off after the ideal window. Well, here's the problem. Once the protein has so much kinetic energy, because remember, the actual protein is made up of all of these amino acids that are in a chain, and those chains are kind of held together by, interactions and bonds between the amino acids. I like to imagine this as a chain of kids that are all holding hands, and every kid kind of wants to go in their own direction, but they're sort of being held together by the hands that are binding them and the structure of the line. But if they're given enough kinetic energy, then there might be enough force for them to actually pull apart and sever some of the hand holding, or in the case of a protein chain, some of these bonds between amino acids. And then that can cause the chain to sort of straighten out, or we like to say become denatured. So the issue here at these really high temperatures is that the proteins become denatured. There's so much kinetic energy that the amino acids are kind of pulling away from each other with enough force that they can physically break the bonds that are holding the amino acid chains into the right three-dimensional shape. Another factor that can readily affect protein activity is pH. So we need to remember that pH is ultimately a measure of the hydrogen ion concentration in a solution. When we have lower pHs, we have higher concentrations of hydrogen ions. And when we have lower pHs, we have lower concentrations of hydrogen ions, but we have a greater amount of hydroxide ions. Typically what we find for proteins is that they have sort of a sweet spot. They have a pH range that is ideal for them, and they do well in that pH range, and they don't do very well when you start to deviate too far in either direction. The majority of proteins are going to do best around a pH of 7, but that's not true of every protein. There are some proteins, for instance, proteins that you might find in your stomach that actually do better in acidic environments, okay? But I would say the majority of them are going to do best at a neutral pH. The reason why has to do with the abundance of charged ions. So kind of imagine that at a low pH, you've got a ton of these positively charged hydrogens, and at a high pH, you've got a ton of negatively charged hydroxide ions. Well, here's the issue. These charges can interact with charges that are on the side chains of the protein. So kind of imagine that we've got, again, this, folded up chain of amino acids. That little dashed line represents a bond holding those together. And these amino acids have side chains that might have charges to them. So let's just imagine for a minute that there is a negative charge on this amino acid. As this hydrogen ion whizzes by, because it has random movement, it's going to be attracted to that amino acid, and it might pull it with it as it moves. If you have enough of these charges around, it might allow for those ions to actually pull apart the protein because of those interactions. Same thing with the negative charges. They can interact with the positive side chains and exert sort of that effect as well. So what we find is that, if we get either too basic or too acidic, we end up with the same effect, which is that in both cases, the protein becomes denatured, it loses its three-dimensional shape, and it can no longer interact appropriately with its ligands anymore at that point. There are actually other molecules that themselves are going to exert an effect on the protein. We have substances that are called inhibitors and substances that are called activators. Kind of as the name would suggest, inhibitors are going to hinder protein function when they bind. On the flip side, activators are going to promote function when they bind. Really quickly before we walk through these, I just want to kind of show us the base model image that we're going to be building off of in this little table. So in our image, this shape right here is the protein as labeled. And then the binding site, of course, is where we want our intended ligands to bind. Okay, so these are the two different ligands that we'll kind of see at various points here. Now, one thing we haven't mentioned before is that proteins will often have another place where things can bind called the allosteric site. So the allosteric site is on a different spot from the binding site. And what it can do is it can make it harder or easier for the ligands to bind, okay? All right, so with that in mind, let's go ahead and look at this table. And let's start with the inhibitors first and see what are our options for turning the protein off and making its function stop. Two different kinds of inhibitors will help us do this, one of which is called a competitive inhibitor. Basically, a competitive inhibitor is going to compete with the ligand for the binding spot. What happens here is that the competitive inhibitor, which in this picture looks like that red stop sign, it binds to the binding site, and prevents the ligand from binding. You can kind of see looking here that this doesn't appear to fit. It doesn't have a good specificity, it doesn't have a great affinity, but it is still able to prevent the other ligand from binding. Okay, so by being in this location, the competitive inhibitor is going to prevent the binding of the ligand, and it won't be able to cause the correct changes in the protein. So this competitive inhibitor doesn't have specificity for the protein. The protein isn't going to change shape and become active when it binds, but it is going to block the correct ligand from being able to get to that space. We also have the option of non-competitive inhibitors, also known as allosteric inhibitors. So what these do is these are going to bind to the allosteric site. So they're not binding to the binding site where the ligand would normally bind. But when they bind to the allosteric site, this is going to cause the binding site to become distorted. So if we look here, we can see that the allosteric inhibitor is this red triangle. When it binds to the allosteric site, we can see that the binding site has now changed shape. It was originally sort of that square shape, and that was going to be helpful because the square shape was going to accommodate this ligand right here. We can see that that ligand would clearly fit in this space, but it's not going to fit in this newly modified space after the allosteric inhibitor has bound. Okay, so the allosteric inhibitor isn't competing with the ligand for the binding spot. It's binding to that allosteric site, but when it binds to the allosteric site, it distorts the binding site so that the ligand cannot bind. It's going to still have the same effect, which is that protein isn't going to be able to function. All right, activators. So activators are going to help promote protein function. They're going to make it easier for the protein and the ligand to come together. One way is through something called a cofactor, and sometimes they're even called coenzymes, depending on what exactly is making up this substance. I put this here on the table because its strategy is similar to the competitive inhibitor, but it ends up having an opposite effect. Basically, the cofactor is going to bind to the binding site. And that's why it's similar to the competitive inhibitor, because the competitive inhibitor also binds to the binding site. But in this case, it's not going to block the ligand. In this case, binding to the binding site acts as a cushion. I'm going to put cushion in parentheses since that's not really a scientific term, to provide a better fit between the ligand and the protein. So we can see in this image that the blue circle is the ligand. It's what we want to bind. It doesn't really appear to have the best fit with this protein, if any fit at all, right? However, it does fit nicely once we factor in the cofactor. The cofactor is going to bind to the binding site first, and it's going to create this cushion that then creates the perfect space for the ligand to bind. In some cases, the cofactor is a nice little addition where it's like, oh, we just got a little bit of a better fit. Everything worked without it, but it works a little bit better now. And in other cases, the cofactor is absolutely critical. We're not going to get any binding occurring if the cofactor isn't there. We also have allosteric activators, which are kind of the counter to the allosteric inhibitor. The reason that they're similar to the allosteric inhibitor is because they bind to the allosteric site. But while they bind to the same place, they have the opposite effect. Same thing we saw between the competitive inhibitor and the cofactor. So it's going to bind to the allosteric site, which will stabilize the shape of the binding site. So in this case, we can see that the binding site of the protein was not adequate before we had the allosteric activator. You can see that this shape would not accommodate the ligands, but once the allosteric activator is in place, it causes the shape of the binding site to be correct and to be able to receive the ligand, okay? So kind of the things you need to really focus on here is, where does this thing bind and what effect does that have? For example, competitive inhibitor, where does it bind? It binds to the binding site. What effect does that have? Well, it prevents protein activity because it's blocking the binding site from the ligand, okay? If you can do that with each one of these things, the competitive inhibitor, the non-competitive inhibitor, aka the allosteric inhibitor, the cofactor, and the allosteric activator, then you're in pretty good shape.